So we need to the lights, yeah. So then that would be there on the that's good left. Okay, good morning. So I guess that we can start, and thanks for coming. I guess the rest of you are still celebrating the Cubs win, right? So thanks for coming today. So as you know, we are going to review the cardiac muscle physiology, and here is my information. Please contact me with any question that you may have. So as you already know, the function of the heart is to pump blood through the circulatory system. So this function will depend primarily upon the contraction and relaxation properties of its muscle cells. So the goal of today's lecture is to understand the control of contraction and the mechanisms underlying degradation of contractile force, okay? So as you remember when you took your histology lectures, the cardiac muscle shares structural and functional properties with the skeletal muscle. And that is, as is showing in this cartoon, they are striated, right? So that means that they do have the thick and the thin filaments, and they are arranged into sarcomeres. So they also, as we'll see later, they do have T-tubules and sarcoplasmic reticulum. And actually, the cardiac muscles are similar to the type 1 skeletal muscle fibers, and that is because they depend on oxidative phosphorylation. That's why they do have numerous mitochondria, and actually around 30% of the content of the cardiac muscle cells is formed by mitochondria. So then they are highly resistant to fatigue, a property that you would expect for the heart to function. But also they are highly dependent on continuous supply of oxygen. There are some differences between these two types of muscle, and one of them, as you can see it here, the cells are short. And remember that when we were talking about the skeletal muscle, depending which muscle we are talking about, the length could be from few centimeters to tens of centimeters, right? But in the case of the cardiac muscle cells, they are short. Usually the length is about 100 microns, and they branch, as is showing here, and they interdigitate between them. Actually, well, here I have a cartoon, and actually this is a photograph, a micrograph, taken from the surface of the ventricle, from the mouse heart. So you can see how the shape of the cells. So, but also, as is illustrated here, there are some strong union between the cells, and this is what is known as intercalated disc. Also, I know that you reviewed this in your histology lectures, and you remember that the intercalated discs are the sites where the cell-to-cell communication occurs. So we have three different types of connections: the zonular adherence, where the thin filaments attach. We have the macular adherence of desmosomes, that is where the cells bind together. And actually, these two types of junctions are considered as a physical couplings, because it's here where the cells mechanically pull on each other, okay? So we have another type of connection that is showing here as the gap junctions. So the gap junctions are considered as a functional couplings because they allow the electrical signals to spread between the cells, right? So then we know that the presence of the gap junctions assures that the heart muscle can work as a synchronized unit. I'm talking about as a syncytium, right? So then, unlike a skeletal muscle, cardiac muscle is fully recruited at all times. So we can consider that the cardiac muscle being as a one giant motor unit. Okay, once let's say that there is an action potential in the SA node, then all the cells will be excited. Okay, questions? Okay, so as I said before, the cardiac muscle is striated, and here is a representation of the arrangement of the thick and thin filaments into the sarcomeres. Remember that I used this cartoon when we talk about in our lecture of a skeletal muscle. And then because we have the similarities with the skeletal muscle, then you can assume that they will follow the same sliding filament mechanism that I described during our skeletal muscle lectures. And that is that the sarcomere will shorten by the sliding of the thin filaments over the thick filaments. Remember that I show you this animation. So, so then the sarcomere shortens its length, but the length of the myofilaments doesn't change, right? Remember that? So, and we also mentioned that this is possible thanks to a series of chemical reactions that will result in the cross-bridge cycling. Remember also this cartoon that we use in our skeletal muscle lecture? I'm not going to describe the whole cross-bridge cycling because you know already this material, but I want to remind you or to emphasize, as I did during our skeletal muscle lecture, that this cross-bridge cycling will occur as long as ATP and calcium is available, okay? And also, as is the case in skeletal muscle, the regulatory step for the cross-bridge cycling is the calcium binding to troponin, okay? So, one difference between the skeletal and the cardiac muscle is that the troponin is not completely saturated by calcium. That is the case in a skeletal muscle. There is always there will be always troponins that are going to be free to bind calcium. And this is an important feature of the cardiac muscle cells because it can help to regulate the amount of contraction, the strength of contraction that the heart needs to develop, okay? So also we talk, as you remember, that in a skeletal muscle that there is some specialized membrane systems that will participate in the excitation contraction coupling. You are familiar with this cartoon that also I presented during our skeletal muscle lecture. And then this is the similar cartoon for cardiac. So as you can recognize, there is high similarities between these two. So this is a transversal cut. You can distinguish the myofibrils, the sarcolemma, and you see how the invaginations forming the T-tubules, also the membranes forming the sarcoplasmic reticulum, and these elongations at the end when they come closer to the T-tubules that are called the terminal cisterna, right? So we have the same structures in skeletal and cardiac, but also you can tell by these cartoons that there are some differences, and I have it, some of them written here. You see that now in cardiac, the SR is less dense as compared to the skeletal. There are different localization of the T-tubules. For the cardiac, we have that they occur at the C line, where in the skeletal, there is they localize in the junction of the A and I band. Also, as you can see here, the diameter of the T-tubules in cardiac is greater, like 200 nanometers compared to 30 nanometers. And this is what explains, for instance, when there is an increase in extracellular potassium, remember hyperkalemia, why the skeletal muscle is more sensitive to the effects of hyperkalemia, because you can imagine that now here we have a less volume, so potassium accumulates really easily here than in cardiac. Another main difference is that the presence of dyads in cardiac compared to triads. Remember, for a skeletal muscle, a triad is formed by two sarcoplasmic reticulum cisterna in close proximity to the T-tubule membrane. And actually, I used this cartoon, remember, to show you a different view, right? This is more transversal compared to the longitudinal view. So we saw this in a skeletal muscle, but as I said, for the cardiac, we have a dyad. That means only one sarcoplasmic reticulum cisterna comes in close proximity to the T-tubule membrane. So this is here, but you can observe here another one. And actually, sometimes this sarcoplasmic reticulum cisterna could come in close proximity to the surface membrane, to the sarcolemma. So do you remember why these structures are important? Or what occurred in these structures? What phenomenon occurs there? Come on, say it. Say it, you have your notes there, right? And doesn't matter if it's not the right answer. Is where the calcium release occurs, actually is here, right? Where the excitation, contraction, coupling takes place, right? Remember that it is here where some proteins are going to transduce the electrical stimulus into a mechanical one. Do you remember now? Yeah? And actually, I have some cartoons here. So here I have the key players for the easy coupling in skeletal and in cardiac. And as you see, we have the same players, the DHP receptor inserted in the membrane of the T-tubule, and then we have the ryanodine receptor inserted in the membrane of the sarcoplasmic reticulum, right? We have both. But one of the main difference between the skeletal and cardiac easy coupling is the calcium handling. Remember that I told you that for the skeletal muscle, actually the DHP receptor works as a voltage membrane sensor. Remember that it's not really the calcium that flows through the channel is basically minimal. What occurs here is once they sense the change in voltage, it will suffer a conformational change, and this will detect it or will trigger the opening of the ryanodine receptor. While in the cardiac, as I have it illustrated here, actually there is the influx of calcium through the DHP receptor that will activate the ryanodine receptor, and this will release calcium that is needed for contraction. Then we are talking about that for the skeletal muscle, there is a process that is referred as a voltage-dependent calcium release, while for the cardiac, we have a process that is calcium-induced calcium release. Okay? I think that some of this material you have reviewed already, right? In heart lectures? Is that true? Yeah, right? Okay, so you are familiar. So actually, let me tell you that unlike skeletal muscle, cardiac muscle cannot contract in the absence of extracellular calcium. See, and I think I remember I told you if you don't have extracellular calcium and you have a skeletal muscle fiber and you stimulate that electrically, the skeletal muscle will contract. But if you have the cardiac muscle in the same conditions, if there is no extracellular calcium, doesn't matter how high you electrically stimulate that cell, it will not contract. So that tells you that how the cardiac easy coupling needs the influx of extracellular calcium. Okay? Questions? No? Actually, the calcium that comes through the DHP receptors during contractions, during normal contractions, is about 20% of the contributes with 20% of the rise in the intracellular calcium. So actually, if the heart needs to increase its strain of contraction, then more calcium can come. So that means that this percentage could be raised. Okay, so that means that the DHP receptor is a major regulatory site for the cardiac function, and as we'll see later, this can be affected physiologically by, for instance, when we have sympathetic stimulation pharmacologically using agonists or antagonists of the DHP receptor, but also pathologically, right? In conditions, for instance, like ischemia, this is one of the targets that is going to be affected. Okay, questions? No? Okay, so we have talked about that calcium is needed for contraction. You know, this is true for skeletal, for cardiac, but also in order for the cell to relax, calcium needs to go back to the resting levels, right? And I have here this cartoon to put this in context. So you know that the key players in this calcium balance are the DHP receptor and the ryanodine receptors, right? They will contribute to increase the calcium concentration in the cytosol, that then it will combine to the myofilaments and produce contractions. So then this calcium, in order for the cell to relax, needs to go back to either the extracellular space or inside of the sarcoplasmic reticulum. And here in green, I have the mechanism in order to do that. So here represents the calcium ATPase that will put the calcium back into the ESR. And also at the level of the sarcolemma, we have this calcium ATPase and then the sodium calcium exchanger that they will contribute to extruding calcium towards the extracellular space. And in less degree, we have the actions of this mitochondrial uniportin that it will take some calcium into the mitochondria. So then I think that now it's clear that the cytoplasmic calcium concentration will depend on the amount of calcium stored in the SR. That also could be affected by the heart rate. The heart rate could affect the influx of calcium, or the calcium that is being, how much calcium is being released towards the cytosol. And also, as I just said, the amount of calcium entering from the extracellular space. Okay? So now let's talk about, I told you that the goal of today's lecture is to understand how the cardiac muscle can graduate its contractile force. We described some mechanisms for the case of a skeletal muscle. Could you mention one of these mechanisms that the skeletal muscle uses to graduate the contractile force? Recruitment, right? Recruitment of what? Recruitment of fibers through the recruitment of motor units. Remember that we talked about if the muscle needs to develop some tension, some motor units will be recruited. If the muscle needs to increase its amount of tension, it will recruit more motor units. Remember that? So do you think that the cardiac muscle can use the same mechanism? No? Why not? Because the presence of the gap junctions, right? I have this animation illustrated that if you inject a cell, right, with a fluorescent dye, and the cells are communicated through gap junctions, the neighbor cells will get stained or will get this fluorescent dye, right? So it's the same situation that occurs in the cardiac muscle. Because of the presence of the gap junctions, you cannot use recruitment, right? Because once a cell contracts, the rest will follow, right? So as I said at the beginning, so then you can consider the heart to be as a giant motor unit, that it will be working at once, the whole muscle. Okay, so there we talk about another mechanism for a skeletal muscle. Remember that, or you have there in your notes? Summation and tetanus. We said that skeletal muscle can use one of these two mechanisms in order to increase its force of contraction. I used this cartoon during that lecture, and you can distinguish that if you apply a second stimulus before the twitch has ended, so the twitch twitch will be of greater magnitude in terms of tension and so on, as is illustrated here. But if the frequency is too high, actually the muscle will respond, showing this increase in tension. You see this smooth and steady increase of tension, and we refer this mechanism as a tetanus, right? So these are some mechanisms that the skeletal muscle use. Do you think that the cardiac muscle can use summation and tetanus? No, okay, that's true. So the cardiac muscle lacks summation, okay? And the reason is, one of them is the duration of their respective action potentials. I have it here in red, the action potential for the skeletal muscle, and in green, the action potential of the cardiac muscle. As you can see, the durations are quite different, right? Between 1-2 milliseconds compared to 100-200 milliseconds. So because of these long action potentials, you know already, you already reviewed the material, we have this long plateau that will result in a long refractory period, right? And also the other situation is that the duration of contraction that I illustrated here is basically the same, the same duration as the action potential. So as you can see it here, the contraction is almost ended when the action potential finished. So actually you apply, only here is when you are able to apply the second action potential, so that's why the cardiac muscle cannot experience summation or tetany, right, or tetanus. So actually this is good, right, because imagine if the heart could go into tetanus, this will jeopardize the function of the heart, right, as a pump. So this is a good feature. So then we have seen that cardiac muscle cannot use recruitment, cannot use summation and tetanus as mechanisms for graduate the contractile force. There is another mechanism that the skeletal muscle could use, or actually affects the amount of tension it can develop. Remember that when we review our length-tension relationship? Yeah, so now let's see how is the length-tension relationship for the cardiac muscle. I'm talking about the change in the initial fiber length. Okay, so here also you remember this curve. We discussed this in the skeletal muscle lecture. So here we have the skeletal length-tension relationship. We said that the active tension, we said that it was a bell shape, right? And why is a bell shape? Come on, wake up. It's here, right? Remember that this will be the result of the different degree of overlapping between the myofilaments, right? Now this makes sense, the curve here, having basically no overlapping, then the muscle cannot develop tension, or here, even though there is too much overlapping, so the number of cross bridges is diminished, right? So you have less amount of tension. We also said that in the case of a skeletal muscle, the skeletal muscle will be operating in the optimal length where it can develop the maximal amount of tension, as is illustrated here. So usually there is this range of operating range for the skeletal muscle, and if you think about it, usually the length of the skeletal muscle will be determined by the insertions into the bone, right? So usually it puts the length of the skeletal muscle in around lengths where it can develop the maximal amount of tension. So now let's see how is the curve for the length-tension relationship for the cardiac muscle cell. And I have that relationship illustrated with this red curve, as you see it here. It's also a bell shape, but actually the cardiac muscle does not normally operate within the descending limb of this curve. And the reason is because the cardiac cell is way much stiffer than the skeletal muscle. So this is a good thing because that guarantees that in normal conditions, the heart cannot be overstretched, right? Because the stiffness of as being a good property of the cardiac muscle cell. So then the difference is that the cardiac muscle cell always operates in this ascending limb of the curve. That is that the resting cardiac muscle fiber length is less than its optimal length. Remember, that's a difference compared to the skeletal that is always at the optimal length. The cardiac muscle cell is always less than the optimal length. And look what it happened. It has benefits to be working below the optimal length. Let's say that we have our cardiac muscle at this length, and once at this length, it will produce this amount of tension. Now, if we stretch or increase its length just a little, look how the amount of tension increases. We have a greater increase. See, just with a small increase, you accomplish a much greater increase in tension. So, and this is what is stated in the Frank Starling's law, that it says that increased stretching of the myocardial fibers will result in a stronger contraction, as you can observe here. And this is a fundamental property of the cardiac muscle. Okay, questions? Okay, so this figure is exemplifying the length-tension relationship of a cardiac muscle cell at the level of the sarcomeres, but let's say that we have the same relationship if we see the whole, in this case, the whole, it could be the whole ventricle, right? It could be left, right, or the atria in less degrees. So here, as you see, we have the active component, as we just saw previously, and that occurs during systole. And also here I have the passive component, right? And you can see how when you stretch the muscle, basically there is no increase in this passive tension up to one point that there is a drastic increase of the passive tension. And this is what I said before, confirmed by the properties of the titin and the connective tissue. I have here just to remind you, right, the titin, that is this structure in red, is what maintains the precise structural arrangement of the thick and the thin filaments, and at the end is what it gives the stiffness of the muscle, right, in connection with the connective tissue. So, and this is a property that you want to observe in the ventricle, right? Because, for instance, if for some reason there is an increase in the end diastolic volume, right? So this will, the action of this properties, the passive tension, will avoid the overstretching of the heart. And then when you increase the diastolic volume, then it will result in an increased stroke volume, as I have it illustrated here. I have here some factors that could affect the length of the ventricular muscle, and it could be that if you have a stronger atrial contractions, if you have increase in the total blood volume, increase in the venous tone, even increase in the on the pumping action of the skeletal muscle. And for instance, this occurs when you are exercising, right? And so this will increase the venous return, and this is opposite that it could happen when you are standing. In a standing position, you have a decrease in the length of the muscle because a decrease on the venous return. So these are some factors that, as you can see, could affect the length-tension relationship. Questions? No? Okay, so now let's talk about some of the events that takes place during contraction, okay? So in order to do that, I have this cartoon that exemplifies the cardiac muscle. In my example, I'm going to use, for instance, the left ventricle, but what we are going to describe, it applies to the right ventricle or the left atria, right atria, okay? But let's say that we choose the left ventricle. So we start in the resting conditions when the muscle is in diastole, right? So that means that the ventricle is relaxed after ejections. That means that the aortic valve is closed and the mitral valve is about to open, right? So from here, we go to the next stage, That is that now the muscle has been stretched, and this is because a preload has been added. And this preload is the results of the end of filling. I'm talking about the end diastolic volume. So then, as you know, because I think that you already reviewed this, the preload is the extent to which the muscle is stretched before the onset of contraction, right? As is illustrated here. So then we go to the next stage, and we still have our muscle resting, is stretched, but now an afterload has been added. So that means that the ventricle has started to contract, but both valves, the aortic and the mitral, are closed, right? So at this point, the ventricle hasn't generated enough pressure to overcome the pressure from the aortic valve, right? So then the afterload, we can think as the resistance that the ventricle has to overcome to eject the blood during systole, right? So then, and finally, we go to the final state, that is the ventricle contracts, and doing that, the afterload is lifted, and that means that the left, there was a left ventricular ejection into the aorta. Okay, so then you can see how the mechanical steps that involve the contraction, in this case we described for the left ventricle. Okay, questions? No? Okay, so then here we have that in terms of the mechanism for graduation of the contractile force, we see that cardiac muscle cannot use recruitment, no summation and tetanus, but it can use the length-tension relationship that is considered as an intrinsic mechanism, but also it uses change in contractility that is considered as extrinsic modulation. Okay, I think also you review some of this material in your heart lectures, and you know by now that the contractility is the measure of the force tension developed by the muscle fiber at a given initial fiber length, right? It's also known as a inotropic state. So then how contractility can be altered? We said that this is one of the mechanisms that the cardiac muscle uses. Well, this can be done by the nervous and hormonal inputs and by drugs. And I think I have this graph to exemplify that. Here we have again the length-tension relationship, right? We just saw that basically the heart operates in this ascending limb, obeying the Franz Starling law, right? So let's say what happened, and if we add some sympathetic stimulation. So now look, now see that our curve is shifted to the left, right? This is under sympathetic stimulation. If we think about the ventricles, we say that at some particular length, now that it could be determined by the end diastolic volume. Now, if you have the influence of the sympathetic stimulation, look, without changing length, see this, without changing length, now, because you have sympathetic stimulation, now the heart will respond with a graded amount of tension that will be transduced in an increase of the ventricular pressure. You see that? And also, here we can use the opposite example. Let's say that you are working with a heart that is, its function is compromised, for instance, in the case of heart failure, right? You see at the same distance, when you can achieve this amount of tension in normal conditions, now you see that at this distance, this length, you can obtain less amount of tension. So now you can see here the relationship or the playing of the length-tension relationship or the contractility. Do you see that? See contractility increasing without changing the length of the cardiac cell. Yeah? So now, as I said before, you see that both mechanisms can take place or can work simultaneously. Okay? Questions? Okay, so then you know that if there are some agents that increase the stenocontraction, they are referred as a positive inotropic agents. But if there are agents that weaken the force of contractions, they are referred as a negative inotropic agents. And both of these types of agents are usually used to treat different cardiovascular conditions. So at some point, you are going to be working with these agents when you treat your patients, right? So I have here some examples of the positive inotropic agents, catecholamines, cardiac glycosides, xanthines, and also I listed some examples for the negative inotropic agents. And as you can see, either if they increase or decrease contractility, they can accomplish that through a different mechanism. At the end, the final action is the same for the positive or the negative agents, but you see they can achieve that through a different mechanism. And I will show you some examples in the next slides, but the contractility at the end can be modulated by affecting or altering the amount of cytosolic calcium available for contraction, also by altering the affinity of the myofilaments for calcium, and also could be by altering the number of myofilaments available to participate in the contraction process. For instance, if you think about an infarction, right? The infarction zone, you know that most of the fibers are going to be dead. They will have a necrosis, right? So that will decrease the number of myofilaments that will participate in the contraction. So at the end, altering all these factors will alter the rate or cycling of the cross bridges. So at the end, contractility, it will affect finally or will alter the rate or cycling of the cross bridges. Okay, so that's how contractility is being modulated. So here I have some examples how some positive inotropic agents can act. So here you are familiar with this cartoon. So let's say that in normal conditions, control conditions, calcium is being increased in the cytosol, and this is here we have a temporal course of that increase. Here we have our calcium transient and its corresponding contraction, right? Or increase in amount of tension. Okay? So now let's say that if we challenge this cardiac cell or cardiac muscle with sympathetic stimulation. Let's say that we use a beta adrenergic stimulation, and we can do that if we apply isoproterenol to these cells, and you know that isoproterenol will activate the protein kinase 8 and the CAMP kinase 2, right? So what happens when you activate these enzymes? I think you saw this in heart lectures, ANS, right? So do you remember this will come and phosphorylate some proteins, right? So the proteins that are being phosphorylated are the DHP receptor, as is illustrated here. So the phosphorylation of the DHP receptor will result in more calcium influx. Remember that I said before, instead to be 20%, maybe it's going to be 40% of calcium coming through the DHP receptors. Also, these proteins, these enzymes will phosphorylase phospholamban that will increase the recapture rate of the calcium ATPase, right, CERCA. So increasing phosphorylating these two channels will result in more calcium being accumulated in the sarcoplasmic reticulum. If there is more calcium in the sarcoplasmic reticulum, to the next beat, to the next heartbeat, it will be more calcium being released through the ryanodine receptor, and then we'll have an increase in the intracellular calcium concentration, and this will be reflected into the contractions. So the mechanism that we are, or the effects that we are seeing here with the beta-adrenergic stimulation is increase in calcium concentration inside of the sarcoplasmic reticulum, increase in the calcium being released from the sarcoplasmic reticulum, and then increase in contraction. And then we can observe this when we compare the both temporal courses before and after addition of the isoproterenol. You see that now the calcium transient is of a greater magnitude because we increase the cytosolic calcium, as we see it here, and we see the corresponding contraction. You see that there is more, the contraction is stronger. We see here also that in this response, we see that the speed of contraction and the speed of relaxation has been increased. And also I have it here just to mention that there are other actions of the beta-adrenergic receptor stimulation, especially the beta-1, that is decreasing the sensitivity of the contractile machinery of calcium. All of this will help to shorten the duration of the action potential that is consistent with the tachycardia, right? Excuse me. So this is, for instance, the actions of the beta-adrenergic stimulation that is a positive inotropic agent. So now I will show you that another positive inotropic agent, but through a different mechanism. And this is when we use some cardiac glycosides. In my example, I'm using digoxin. Okay, do you know what are the actions of digoxin? It's a blocker of the sodium-potassium pump, right? Correct. So here we have the digoxin blocks the sodium-potassium pump, and this will make that sodium inside the cell will increase, right? The concentration increases. By increasing the sodium concentration, the activity of the sodium-calcium exchanger is slowed down, and this will result an increase in the cytosolic calcium. By increasing the cytosolic calcium, there will be more calcium available to be used for contraction, but also to be recaptured and stored inside of the sarcoplasmic reticulum. Then, for the next heartbeat, we have more calcium being released, and then more cytosolic calcium available for contraction. At the end, I have it here that the actions of cardiac glycosides will result in an increase of cardiac of calcium inside of the SR, increase of the SR calcium release, and then increase in contraction. These are the same steps that I mentioned for the actions of the beta-adrenergic stimulation, see? But you see that now we ended with the same effects, but through a different mechanism, right? So actually this is, digoxin actually is not so popular, its uses, because increases so much the calcium that at some point is toxic, right? And it will lead to arrhythmias. So it's one of the agents that is not so common in, now by the clinical use. So at the end, the take-home message is that the available intracellular calcium is what determines the myocardial contractility. So therefore, all the factors that modulate intracellular calcium concentration will affect cardiac contractility. Okay? Questions? Okay. So then we're almost done. So you can ask, well, how can you measure the cardiac contractility, right? And you can accomplish that by measuring the ventricular pressure curves. I have here some examples for the left ventricular ventricle, and I have three different cases. So these are the curves in black showing in normal conditions, and in red we have when the ventricle is under the actions of the norepinephrine, beta-adrenergic stimulation. And also in blue represents when the function of the heart is compromised, as it is in cardiac failure. You see how different are the curves, and already you can distinguish all the parameters that are being changed. So you can see one of them is the end diastolic pressure being different, being lower in the case for norepinephrine stimulation and higher in the cardiac failure. Also, the duration of the ejection phase is different, as you can see between them. So then I have it here that when you increase the contractility, you will observe higher shortening velocity, also a highly developed tension peak, as is illustrated here, and also a steeper rise of pressure. Compare this norepinephrine compared to the control or even with the cardiac failure, and this is better appreciated when we take the slope of these curves. So in the case when you have a decreased contractility, you will find a lower shortening velocity, lower tension peak compared control with this from cardiac failure, and blunted pressure rise. So when you measure the slope of these curves is what it will give you the index of cardiac contractility. Also, this is example using the left ventricle, but also you can do the same measurements by using the aortic flow curves. And another method is by measuring the ejection fraction. That one also can give you an index of the cardiac contractility. So this is just to put in context that the autonomic nervous systems can control or can modulate the cardiac contractility. And as I mentioned already, the influence of the sympathetic nervous system has a positive inotropic actions through the actions of the cyclic AMP. We said that activation of the pKa, and then the phosphorylation of the different substrates, as are illustrated here. On the contrary, the parasympathetic stimulation is considered as a negative inotropic agent because this acts mainly in the atrial muscle, in less degree in the ventricular muscle, but its action is by inhibiting this cascade that you obtain with the sympathetic stimulation. And I just want to mention that the parasympathetic and sympathetic stimulation are the physiological means that control not only the inotropic or the contractility of the heart, but also the chronotropic, dromotropic, and lusotropic properties of the heart. Okay? So I guess that then we are ready to do some exercises. Yes? Or shall we go? Is that yes or no? Yes. Okay, so let's do some exercises. So in cardiac muscle, ATP binds to tropomyosin. True or false? False. It binds to myosin, right? The same as it does in a skeletal muscle. What is the excitation contraction coupling mechanism in cardiac muscle? Calcium-induced calcium release, right? Perfect. What prevents tetanus in cardiac muscle? The what? Yeah, the long action potentials with presents a long plateau, and with that a long AP refractory period. Okay, stretching cardiac muscle always increases contractile force. True or false? True, right? Think of a Frank Starling law, right? It follows that. Higher cytosolic calcium levels decreases inotropy. Inotropy, I don't know how to pronounce. Contractility, true or false? False, right? Calcium drives the cross-bridge cycling, remember, then increases the inotropy. And finally, the L-type calcium channels are in the SR membrane. True or false? Where are they? And the T-tube, right? The T-tube membrane. Okay, so we are done. We can go. Questions? No? Okay, so I hope that everything is clear. So you have questions, just email me, okay? Thank you. I think I will see you for a smooth muscle lecture, okay? Thanks.